channel for another nighttime live stream to investigate some mathematical puzzle-like things that some of which I already invented and tested that I'll present to any of you who want to try solving a mathematical puzzle thing, and some of which I haven't done many deductions on yet, and since I was fiddling around with numbers in a way that I thought some viewers in my audience may find interesting, I figured why don't I show you a little bit of the process that I've been going through in some of what I consider my free time, although it is slowly contributing to various other sorts of mathematical growth and learning, and possibly adding up to some future episode topics on my main combo class channel. At the moment, I'm treating it like a free time exercise, experimenting with designing a particular type of puzzle. Now, the type that I'll show today does have very specific rules, but it is in a wider category of puzzles, which are essentially let me just show a visual of this and make sure that the background's working to give an example visually so I don't have to just try and describe it with my hands and arms. Here, let's see if it's actually moving. Oh no, it's frozen. Okay, I gotta bring it back 1 second. Gotta recapture that screen. It's always frozen for some reason once I start the chat again, or start the stream or something or another. There we go. Now I think it is unfrozen. These are just some structures that I made in a new document. This document doesn't contain all the notes I've been taking about these, but these will give some good visual backdrops to begin with, and then I can copy paste some of these grids so that we can use them to investigate some other things. And I'll put myself over on this side and give ourselves a little bigger view on these. And to begin, let me explain the types of puzzles I've been working on. They are numbers in a grid, but what most people think of when they think of numbers in a grid and a puzzle is Sudoku. And this is quite different than that in terms of what rules it follows. One main distinction about the overall puzzles I've been investigating is that they don't contain, typically, at least in the first batch I've been testing now, repeats of a smaller range of numbers. They contain singular versions of a larger range of numbers. And for reasons you'll see in a moment, the puzzle that I'm mostly showing today has a number range of 2 through n+1, where n is how many squares are in the grid you're doing, because you could do this on different sizes of grid. And the reason it starts at 2 will be clear in a minute, but it's essentially that all the whole numbers from 2 upward through the point that fits will each appear once in a single cell. And the rules beyond that, I've experimented with various sorts, but I found one that generated some very neat puzzles. For example, a simple rule set that theoretically this is enough information, just a 9 there, no other numbers given, and for this size this would be the numbers ranging from 2 through 13, each appearing once, with some simple rules that makes this correspond with only a singular solution. And the rules that I was following in particular here, let me explain in 1 second. First, I just have to real quickly note, because I forgot to note at the beginning, I'm very excited for the next main project I'll be putting out being the official intro to our new grade -3. And part of why I'm facing just the wall where it says combo class spray painted, and hopefully the view isn't just the last 3 letters like it sometimes is. We're in this corner because the other part of the classroom has some new clocks and other secrets that I'm saving for that episode that I don't want to reveal quite yet. And that will be coming on my main combo class channel in less than a week. Also, make sure that you've checked out the grade -2 finale on there. Now back to our puzzles. The rules that I was using for these puzzles begin with first me trying rules where numbers must be near certain things like factors of themselves or numbers that are nearby additively like themselves plus or minus 1. And that made it trickier to expand how many grids were possible in the realm of the puzzle. For example, if I said numbers had to touch as neighbors in some way, like this would be touching these 8, all of their factors, there would be a certain size of grid where that would be impossible to have the number 2 incorporated, because 2, eventually we would have too many powers of 2 to cram around it. Or for 2, if we were doing multiples of it, we would pretty quickly hit a point where we wouldn't have enough evens, or there'd be too many evens to force around it. And so I realized I had better luck when I looked at rules where numbers must avoid certain things, where there's restrictions that I sort of in my head as a nickname, because we will use some helpful nicknames, is numbers being allergic to other types of number. And if they are allergic to the other type of number, then they cannot be neighbors, including diagonally 1 cell apart from that other one. For example, these are the neighbors of the 9 that's written in there. And the rules that we're going to be looking at today, because they generated some good puzzles and I want to investigate them further, are numbers cannot be neighbors with any multiples of themselves. They cannot be touching any other cell that contains a number that is a whole number times themselves. And they also cannot be touching any numbers that are 1 larger than themselves. And those are all the rules. With just those rules, there's actually only one solution that lines up with this 9 right here. And the only other, apart from rotations or reflections, apart from symmetries of the same thing, the only other truly distinct solution that fits at all when looking at the numbers 2 upward on a 3x4 grid like this has this as a singular clue that theoretically gives you all the data to calculate the others. A 5 there instead of a 9. Now, if you'd like to calculate these, feel free to do it, because don't worry, during this stream, I'm not going to spoil the answers to these particular sizes. There's other sizes I will show the answers to, but for now, I want to leave these as a puzzle to my viewers. And there are 2 reasons why I want to leave it open for now. One is that I'm curious if any of you can solve it and to what degree of what you'd call guess and check you had to use. That is ambiguous here, but essentially how many layers of, well, if this was there, then that would be there, and then that would be there, and that was a contradiction. Only 1 layer deep would be like this number itself would contradict any square except it living here, or and stuff like that. This will need more than that, where you sort of imagine, well, if this was here, that would be there, and that couldn't be there, or extensions like that. And if you want to try solving them, you probably do want to watch the rest of this live stream where you'll see on different sizes me put together some of the clues or the types of logic you would use to start cracking one of these. Now, the other reason I want to leave it open is because maybe some of you have some neat ways where a particular step, you had a clever or simple way of deducing something, and I'm curious to hear those in comments now or later, because some of the steps for me to check that these were the only 2, apart from reflections and stuff and rotations, the only 2 distinct solutions and what the other numbers in them are for this size, a 3x4, is some of the steps I was able to use clever things that were like, ooh, this proves this whole thing just with a step or 2 of extension, and other steps felt a little further into the guess and check, which is a subjective level of territory where it felt like I was sort of having to speed it up. Sometimes I was even just copying multiple things of a grid and being like, these are the 4 possibilities for where this could be. Where do each of those lead to, and which ones are contradictions? Now, to write down the rules, let's just write it down real quick. There are a few ways of phrasing things. And the first big clue I'll note is that pretty quickly you'll realize that from the rule that numbers can't be next to their multiples, you note they can't be next to their factors, because then the rule would be broken the other way around. So, like, for example, 4 not only can't be next to 8, but if it was next to 2, it would break the rule in the other direction, because it would be a multiple of that, so it can't be next to its factor 2 either. Similarly, the can't be next to 1 more than you rule also encodes and implies can't be next to 1 less than you, 1. And that's because, similarly, if you were next to 1 less than you, you'd be breaking the rule for that number. So all the rules we need to write to imply all that are each cell contains, we got to shrink this a bit. Each cell contains a distinct number from 2 through, and then if you were actually writing one of these puzzles, like to print it for someone, you would write the number for the particular grid right here, but I'm writing the general case, which is n plus 1, where n is the number of cells in the grid. A distinct whole number. And let's say each blank cell, because that gives us the option of having cells blacked out. Or you could, sort of like crossword puzzles look, or various types of grid puzzle, incorporate this, having some of the stuff shaded out like they're missing, which essentially lets us use the grid structure in a different shape. If you wanted to, for example, create some weird shape of them connected, you could imagine that on some bigger rectangular grid with all the outside space just blacked out. And so theoretically, they could all fit on some grid, as long as, if we wanted to make it a weird shape, we blacked some of the cells out. Cells cannot be touching, including diagonally, a number that is a multiple of, I guess I'll say numbers cannot be touching, including diagonally, a number that is a multiple of themselves, or a number that is 1 larger than themselves. Now that's all our rules we need. It encodes all of, or implies all of the other rules that we need. Like, normally when I first wrote this, I was like, they can't touch multiples or factors. And then I was like, wait, I only need to write one of those. If I say factors or multiples, it implies the other from the reflexive. Same with 1 larger, could have been 1 smaller. Either would have implied both. So, going about this, one of my first questions was, okay, does this work on various sizes of grid? And it turns out it does, but not every possible size of grid. So then I wondered, what sizes of grid does this not work on? And for now, let's assume there's no blacked out cells, so we're using a grid shape, and that determines how many numbers we're going to. The interesting thing about designing and looking at these is when you go to a bigger size, you get more room for stuff to go, but you also get some numbers that make more stuff have to dodge around in a weird way. Like if your range only went through the number 11, say on a 2 through 11 would fit on a 2x5 little grid, which actually is impossible to make one on. It's too small and various traits don't let it work. Then it doesn't work in certain ways. The 2x5. I'm pretty sure, I might double check that this live stream. That one I haven't double checked yet, but I'm pretty sure 2x5 does not work. But a 2x6 also happens to, I think, not work. Maybe I'll or actually that one I don't need to double check. It has an even simpler proof that the 2x6 is impossible than the 2x5, which seems weird, but the reason is because 2x6 would be the numbers 2 through 13 as opposed to 2 through 11. And introducing the number 12 has a big effect because 2, 3, 4, and 6 are affected by that, as well as 11 and 13. And so now on a 2x6, we can pretty quickly note in our head, okay, 2, 3, 6, or instead of the 6, I could have said 4. You could substitute the 6 for a 4, but we'll go with 6. 2, 3, 6, and 12. None of them can be touching each other. And there's not room on a 2x6 for 4 different things that none of them are touching each other. because if you imagine spreading them apart, you need larger. Now, the interesting thing is, although I'm pretty sure those sizes don't work, the bigger size... Oh, and let me make this actually fit in the screen, because I want, if anyone comes new to the stream, they can actually see what's going on. Uh-oh. Oh, come on. Each time I move the scale, it slides it a bit. Okay. There. Now, the interesting thing is at 2x7, it explodes. There's tons of ways to do it. And something similar happens here, where 3x3 would be too small to work. And the quick way to show it, 3x3 doesn't work for this, is that the center cell is going to be some number that has at least one thing it can't touch. Because even if it doesn't have factors, the number one larger or one smaller than itself will exist. So it has something it can't touch. But the center cell is touching all the others on a 3x3. So that thing that the center cell was allergic to has nowhere to exist. So a 3x3 doesn't work. A 3x4, I find really interesting that there's exactly two solutions, or you'd multiply that by something like 8 or maybe 4 or 16. I'd have to think about it for a minute if you included rotations and reflections of them. And so also I find interesting that they're distinct enough from each other. They have some bits similar to each other, but they're distinct enough that this single number, a 9 there or a 5 there, is enough to imply a single solution, one of each type. Now no rotations or reflections would work. So this sort of gives us one of each type. And the shocking thing about that, to me, is with this 9 here, if I didn't have these simple rules for what was allowed to touch what, and I only had this first bit about how many numbers I'm using, not that next sentence, there would be 11 factorial ways of arranging the other numbers here. Because there's 11 possible blank spots that could be in any of each other's spots if I only had that first sentence describing what numbers we're using. And so out of 11 factorial ways, there is this tiny handful of ones that work as a solution. Now, by solution in my notes, I'm thinking like an array of numbers that works for this. And then by a puzzle, it's sort of like a semi-filled in array of that. Now, if I were to turn this into like a puzzle in a book, I might have a page that was like, here's a clue with another number, if you want the clue, with another one or two filled in, so that you wouldn't have to do too much guess and checky feeling stuff to solve it, and it would be a bit easier to solve. But this is enough information that you can solve it from just this. And by solve, what we really mean, since the scale of what is and what isn't guess and check is subjective, then solve really just means lines up with a singular solution. And in this case, there are only two solutions apart from rotations and reflections. So this is a puzzle for those of you who want to try it. But what I then started investigating is, so on the 2x things, the 2x7 explodes to tons of options. And I probably won't go that deep into the 2x7 today, but I'll show that in once I someday make a main episode about all this on my combo class channel, because the 2x7 has this really interesting trait I realized. And see if any of you can put together by thinking, what would be a really interesting trait about 2x-somethings in general? And maybe it'll be even cooler if one of you thinks of a different interesting trait than the one I'm thinking of. But in general, some of these more vague puzzles I do plan on answering at some point in this grade in a main episode about grid puzzles I've designed. Probably after I do a first one about grid puzzles about star battle strategies. Trust me, even if you don't think you care about this one particular puzzle called Star Battle, that is going to be the main focus of, or using it as a tool to explore general things about games, of the first main episode I will make about grid puzzles. Later we get Sudoku. Star Battle's underrated. And so some of those techniques are applicable to games in general, not just that one. And they're different than Sudoku type. They're almost more similar to some of these things, even though that is purely geometric looking, doesn't involve numbers. Because it does involve things can't touch other things of certain sorts. And so, what I was looking at in the way that the 2x7 explodes is I'm pretty sure we also get an explosion at a 3x5 and at a 4x4. By explosion, I mean going from none or just a tiny handful of solutions to going to tons of solutions. Because remember, like on a 3x5 in general, there are 15 factorial ways to arrange the numbers if we're not following this rule. And so different sizes, we're sort of looking at the weird restriction that makes them maybe have no solutions, or this interesting case with a tiny amount of solutions, or the ones that I'm saying explode. They get really big really quick. Now, even if they explode, we can note for particular grid sizes guaranteed traits about them. And part of what we're going to do in this live stream is look at a 3x5 and a 4x4 and see to what degree we can see if those maybe explode, and mostly what traits can we note about them. Of course, on any of these grids, there's a lot of traits just encoded in these rules. If we wrote them all, it would be, for a given range, this number can touch these, can't touch these. This number can touch these, can't touch these. It's encoded in this main rule for different sizes, but in a 3x5, for example, it would be equivalent to saying, wherever you put the 2, that can't be neighbors with 3 or an even number. Wherever you put the 3, that can't be neighbors with 2 or a 3 even number. And because each one, sort of, this rule gives its own personal rule of what it can or can't touch. What are these letters, by the way? This was a way I was putting in to look at some of the symmetries. Like if there was a single cell filled in with something, and I wanted to know, okay, then I'm going to investigate a different single cell filled in, which ones are equivalent under a rotation or other sort of transformation like flipping. And so, for example, this B is the same as this B if we flip it this way. This B is the same as this B if we flip it that way. If we do both, it could become that B. But these D's are different because they're on the thinner end, the less wide end of the rectangle, compared to the B, which is on the wider end of the rectangle, closer to a corner, and the C, which is right in the middle of the wider end. And if we make larger versions of these, they look kind of neat. Like, let's just see what it would look like for a 6x6. It would look something like A, B, C, C, B, A, B, D, E, E, D, B, C, E, F, F, E, C, and this looks random at first, but look at all the symmetry in it in a minute. C, then these actually get copied in reverse. So this is sort of like if we just put one number onto a 6x6 and we wanted to note all of the transformations that it was the same as under different symmetries, there are this many types. This C is third from a corner on an edge. Same with these. This E is at a particular spot that could be measured as similar as that E under a particular way of flipping it. So, That's interesting to think about when we think about ways things can flip into others. These are hinting at group theory tables where you can see symmetries that many things have in common. And so we will eventually get to a full group theory episode and or live streams. But for now, I'll just note, if you are curious about that type of thing, of what flips it into what, look up things like in group theory, what is the group that describes symmetries of a square? Or what is the group that describes ways of rotating a pentagon? Or stuff like that. Now, here, that was just a way of filling it in, of the same type of symmetry look. But we're going to eradicate that for now, because I kind of have it in my head where, you know, this feels similar to that and that and that, if you look at it a particular way. Now, some of them that are symmetrical are quite important for some of our first notes. Let's nickname some of these. And we're going to look at it sort of like a face, because we're going to nickname that there's two eyes. And later, if it's helpful, we may call this one the nose. But the eyes are where we're going to begin. And the reason why we're going to look into 3x5s with these eyes in particular is that these two eyes between the two of them touch every cell. What that means is there's a lot of combos that are impossible for the two eyes to be. And perhaps we should write some of these possibilities down, or impossibilities rather, where some things to note about these eyes, that this is like an example of the type of weird new strategy that I'm trying to develop of looking at building the puzzles that theoretically maybe if you were solving the puzzle would be helpful. For example, if you were trying to solve one of these at one point in your investigation, it might be helpful to think about what traits do these two have? Like these are sort of the eyes of this one in a similar way, in that between the two of them, they touch every cell. Although you could also say that's an eye with that on this smaller one. Up here, there are other trios that do that, like this plus this plus this. Altogether, the three of those touch everything. But the eyes here are the only case where only two cells between them touch all the others. And this is not a formal name, but maybe it'll be in the game theory dictionaries someday. What we're going to note that I realized about these eyes is that implies that a few things. Eyes cannot be two apart in size. Why is this? Because if they were two apart, the number in between them, they're both allergic to. And so that would have nowhere on the grid to live. So also, eyes cannot be multiples of the same n larger than n itself. For example, eyes cannot be both be even numbers larger than 2, 3 even numbers larger than 3, etc. Because then they would break that rule. We also have eyes cannot share a multiple in the range. So they cannot both have a multiple, a number that is a multiple of both of them in the range. So for example, the eyes can't be a 3 and a 4 because where does 12 live? The eyes can't, in this case, we do go from 2 through 16 if filling this size. And so 3 and 5, nope, where's 15 gonna live? So they cannot share a multiple in the range. These are just things we can deduce from our rules. And the last one, I guess, is a little harder to describe. An eye cannot have a multiple that is one apart from the other eye. So that's like 2 and 5 couldn't both be the eyes because 2 is 6 is something that they both are allergic to in different ways. It's one larger than one of the eyes and a multiple of the other. But these, I believe, describe the different ways we could use that information that the two eyes cannot be allergic to the same number. in this size of grid. Different things happen on a 4x4. See if you can think of some ways that would be easier and some ways that would be harder. The amount of symmetries on the 4x4 was way smaller, by the way, than on the 3x5, because there's more different types here. I'm on the longer end, near the edge, or I'm on the shorter end, or stuff like that. As opposed to the 4x4, really only has corner, edge that's not corner, and middle as the different types, like symmetrically. Once you have one number, though, that fixes it as some of the symmetries. If I have a 4x4 and I put one of the corners, that fixes certain things about the rotations about that solution. And if I have a number that's not on a diagonal, it fixes even more things about the solution. And certain spots of it that are like asymmetrical spots fully fix it. This right here, I had to actually pick an asymmetrical one to fully fix it. If I had told you what this number was in the arrangement instead of that, the whole thing could have been flipped. No matter what the example turns out to be, we know it would be the case that if this is the only clue, it's got to correspond with two solutions, because if that works, the flip works. So these are some we should note here on 3x5s, because it's different on different sizes. So these, and honestly, I always lean toward, if like you want to try designing one of these puzzles, 6x6 has a really nice size because it can be split into a particular amount of 2x2 squares or a particular amount of 3x3 squares. It has quadrants, but it also has like tri-quadrants. And so 6 is really cool, but the number range up to 6 would be 2 through 37, and that's kind of a lot to deal with. So if any of you fiddle around with making these on your own, you may want to try 5x5s. 2 through 26 is a nice range. I've also been analyzing these ranges for how many primes are in the range, and not just low primes, but how many numbers that only are allergic to their neighbors, but not multiplicatively to anything in the range are there. For example, a prime large enough that twice itself isn't in the range. And so numbers like that are going to be ones when I'm designing a puzzle, I'll more often have to give as a given starting number, because they're more likely to be possible here or possible here if I swap the primes. Not always, but more likely than composite numbers that have to avoid more things. And so when I was looking at the ranges, I was thinking about things like in the range 2 through 26. Part of why that's nice of a range to design is that 11 does have twice itself, 13 does have twice itself, so they are allergic to those as well. And the only ones that are only allergic to neighbors, we'll call them minimally allergic numbers in the range, the minimally allergic numbers from 2 through 26 would be 7, no, not 7, we have to start way bigger. It would be 17, 19, and 23. Now, if we go up to 37, it's pretty good, but we would have to note that even 19, 23, 29, 31, and 37 would all have that trait where they're only allergic to their neighbors. In fact, 37 would only be allergic to one neighbor because it's on the top. So 37 would be relatively common that would have to be given as a starting clue, because otherwise it's more likely it could swap with something else and have another solution. And this is something interesting that's going to come up in my full Star Battle episode that'll be a few episodes into grade -3. And something that's going to come up is, can you think of ways that you could use as a strategy the fact that you know there's a singular solution? I mean, apart from just that you have to avoid contradictions, but like the fact that you know it lines up with not 2 different solutions or more, just one. Could you use that strategically when solving a puzzle ever? And that answer will surprisingly be shown some surprising things about that. a few episodes into grade -3 when I officially make my first main episode that is grid puzzle related. To fans of mine who are less fans of grid puzzles, don't worry, there's only going to be 1 or 2 episodes about it in grade -3 and a handful of live streams here and there. But it is a current hobby I have that I was sure at least some of you would find interesting, and I think it would be really good for your brain sometime. It takes a while, so if you're ever bored, if you're ever stuck waiting for an airplane or something, write down one of these puzzles. Pretty easy to remember. If you remember the simple rule, all you got to remember is, okay, it's one of the spots that has sort of offset, like in terms of symmetry, there are less ways we can reflect around. It sort of ties down one of the symmetries, as opposed to, like, if I had given you this, you'd note that we could have flipped it to another solution that must match also. So note it's sort of an offset tile. You can either put as a 9 or a 5, depending which of the two you're trying to crack. And a non-central tile is that one. Now, let's look at what sorts of techniques we might actually use if we were solving an example of one of these. And I guess just to show you an example of a technique, I will note a few things you'd want to consider on different sizes. And I won't do 3x4. I'll use a different one as an example. Let's, for an example, imagine a 4x4, and I'm just going to make it pretty sloppily right now. Just these are different cells on the 4x4 to imagine. These are all numbers. And each of these cells on the 4x4, if we imagine our range on a 4x4 is the numbers 2 through 17 to fit numbers 2 upward, then we note that, okay, 2, 4, 8, and 16 are included. Those all can't touch. Kind of similarly, we have a 2, 3, 6, and 12. None of those can touch each other because although 3 is odd, it's neighbors with 2, and these are multiples of both. And so what this tells us is if we look at quadrants of this, a little 2x2 upper left quadrant, a 2x2 upper right quadrant, etc. for below, each of those quadrants can only contain up to one number of each of these lists because each of those quadrants, all the numbers inside it touch each other. We can't have a 2 and a 3 in the same quadrant, otherwise they break the rule because they're too close. Can't have a 2 and a 4 in the same quadrant. So if you imagine like these cells, you know that contains 1 from this list exactly, and 1 from this list exactly. When it's the 2, it'll be the same one. You can also deduce on a lot of these puzzles that the 6 ends up in the same one as the 4, because if we look in this case, the 4 cannot be next to the 2, 3, or 12. And each quadrant has 1 from each list. And so to have 1 from this list in whatever quadrant has 4, it has to be 6. So on the 4x4, let's make a little note, because we're sort of going up on notes. The 4x4 notes, very similar to the 3x5 notes, but also going to be very different. So on the 4x4, our notes would be, so far, just that those in different quadrants. Those are in different quadrants. And what we noted about the 6, let's combine into this. 2, 4 with 6, 8, and 16 are in different quadrants. Or here, we'll move the with 6 to combine with the rest of the part of this. We'll say 6 is in the same quadrant as 4. And by quadrants, what I mean is a 2x2 that could be described as upper left, upper right, lower left, or lower right, 2x2. So, or if you imagine like we're on a graph and we have the y-axis cutting right here and the x-axis cutting through here, and those are the quadrants of the graph. So 6 is in the same quadrant as 4. And then we can note 3 and 12 are in some fashion, some order, we'll say, some order of 3 and 12 in... Okay, or how can we phrase this? Between 3 and 12, one of those is in the same quadrant as 2. No, 3 can't... No, those can't be 2. Is as 8. And the other is in the same quadrant as 16. That gets rid of that description and includes it. So that we would know on a 4x4 that they have these different quadrants going on. Now, a trickier thing, the quadrants are easier on a 4x4 because there's just 4 of them. And on a 3x5, you can't as easily divide it into squares like that. If I look at just, I want 2x2 squares because those, all the things inside them touch each other. And I want to look at different ones, like little different pockets in it. Well, this would actually take 6 to cover it. I would be like, okay, there is a 2x2 square. Okay, there is a 2x2 square because I want to get them all. Oops. Well, you know what I mean. It would take a lot more squares to tile over this to cover it all. So it's harder with the quadrants, but it's easier with the eyes because, and by easier, I mean for now, what can we deduce? Easier to get information about the possible solutions. I believe each of these has a big web of solutions, but there's also a big, like a lot of patterns within that web of things that it can't include. Now here, we can note that the eyes are trickier here. If we mark these as X's instead of O's, these are the interior cells. And let's actually just give them each a little nickname of what type. These we'll put I for interior. It'll be, I guess, a capital I. Or, those look badly spaced then. Okay, these will be C for center. That fits better. And, or does it? Okay, we'll just spread these out more. Now we get our I for inside. These ones are inside. These ones we're going to call edge. Not to be confused with an E for even. It stands for edge. And just in case people think it means even, let's put an S instead for side. That's what we'll call that one. And we'll call these ones corners. Not to be confused with C for center. And so this is the pattern that we would find in a 4x4 of different types of symmetry, sort of. Or which singular numbers would be equivalent to others under some symmetry. And so from here, the eyes, there's not just 2 things that cover the entire thing between them. You can't even find 3 different spots here that add up to covering the entire grid. There will be something none of them cover. And so to have some that add up to covering the whole grid, we need all 4 of the eyes. So, for example, now, all 4 of the eyes cannot all be even numbers larger than 2. Or it can't be that 3 of them are even numbers larger than 2, and one of them is 1 larger than 2 and is 3. So there's various things that can't happen here, but the eyes are less of a thing we can target because 4 happening is a lot more complicated. Okay, that's a little better. 4 is a lot more complicated than when we have 2 eyes, like the good old 3x5 here. However, I have some bias toward the 4x4 as well, because the 4x4 is just a more square shape. 3x5 is just a more random seeming shape. Despite that bias, the 4x4 has another issue. It includes 17. This one would fit 2 through 16. This would fit 2 through 17. 17's harder. That's one of those ones that it only has a singular thing it's allergic to, 16. So if 16's already taken care of, buried by some other numbers, 17 could go anywhere else. the other numbers have to push it into a particular spot. So it's less helpful tying down a single solution, meaning it's more likely that if you're designing a puzzle where the puzzle lines up with a singular solution, that 17 has to already be given at the beginning. So not necessarily, but more likely. Okay, now I have to go to the bathroom inside really quick, and then I will be back to solve more facts about these. And somebody asks, is there a max? First, I'll answer a few comments here. And somebody says, is there a max size for these? Max size for certain shapes? I don't think there should be a maximum. There's a chance that a certain size doesn't work, even though a smaller size works. I haven't found that yet, but it could happen as new numbers are introduced. But as I imagine, any arbitrarily large grid, or almost all grids, looking at the big scale of it, work. And my logic for that is that the more numbers you have, the less percent of them each is allergic to, and the more room it has to dodge. On a small enough grid, you can't fit them even just with the rule that they can't touch ones that are one away from each other on too small of a grid. And so on a big enough grid, if you were imagining random placements of numbers on a massive grid and seeing if they fit these conditions as a solution, then which is a whole separate question from which of those numbers on it imply just a single solution and could be called a puzzle. But just to see if a particular grid of filled in numbers was a solution, if you were randomly throwing them at a giant grid, it seems pretty likely that you wouldn't even come across the touching one away from each other. Like it would maybe, I'm guessing, become a vanishingly small percentage of numbers on a big enough grid randomly chosen that would end up landing next to one that is one apart from each other. Because each of them still on a square grid has at most 8 neighbors. Now, you could extend things about that, and you could say, for example, 2 ways you could imagine extending the addition rule are they can't touch numbers that are 2 apart from themselves either. Or, it's only 1 apart from themselves, but they can't be within 2 cells of anything 1 apart from themselves. Or some combo. Maybe the cell next to them can't be within 1 of them, but the cell 2 away can't be within 2. And various things like that could create more elaborate rules if you wanted to tie down larger grids to smaller amounts of solutions. However, I think that for a large enough grid, there should be a number of good puzzles that are arrangements of the grid where some of the numbers are given to you and some are blank, that the blank ones can only be filled in a singular way, meaning some way or another you could solve that solution of the puzzle. Now, a big question of mine, since I'm pretty sure that most large grid sizes should work for this, my next question is how many givens do you need? Like on a really big grid, do you need to provide half of the numbers to the viewer to only line up the other half with a single solution? Or can we get more cases that were pretty neat, like this one here, where in these cases, it's like only 1/12 of them I filled in for the viewer, but it lined up with a single solution. Now, I was already finding on some of my experiments that you need to give a lot of numbers for it to line up with a single solution. Like we're going to probably need far more than 1 number as our given in a 3x5 or 4x4. But I don't know that answer of what is the minimum amount of givens for a particular size, or if there's a pattern to that. I don't even know the answer for a 3x5. I do know for a 3x4, the minimum amount of givens is 1. And here, another question here. So there's not a maximum. In fact, there's not even a rule they have to be connected on a square grid. This rule is just neighbors, meaning they can't be touching. you could apply this in a graph theory-like way, not coordinate plane graphs, but the graph theory of ways things are connected, to say, I'm just going to have a bunch of different circles that each need a number, and I'm going to draw lines between the circles that are neighbors with that other one. Or maybe you wouldn't use the nickname neighbors anymore, maybe you'd say connected. And so then you'd say, okay, numbers can't be connected to this or that. Some of those arrangements you could do on a grid, like this could be drawn that way, but it fits on a grid. First, I'm investigating the grid ones, because square grids are pretty fundamental, and they're just a great starting point for this. But you could do this on things like triangular grids or other graph theory things that would be a little harder to draw. You could even do this on a 3D structure, if you wanted to, say, have 4 different 4x4 grids, and say that each of, I'm not positive this has a solution, but for some size it probably does, a 4x4x4, because you have a third dimension basically. You say this one's the top layer, this is the second highest layer, this is the next highest layer, and they're also neighbors with whatever rule you make for how above counts. And so you could even make them fourth dimensional if you get more abstract and less of a visualization of picturing it in your mind like slices of a cube. You would need a whole, you can make a 4x4 grid of 4x4 rectangles and say, okay, these are the layers of cube A, these are the layers of cube B, cube C, cube D, and these cubes make a hypercube. So there's not many limits to what we could do here. In fact, graph theory is where you'd want to look if you want to get more abstract with the connections. But square grids can do a lot already, and if we were going to try another, the next thing would probably be triangular or hexagonal grids before we go even beyond that. Now, somebody notes large grids have a lower ratio of primes total. Is that irrelevant? Now, they have a lower ratio of primes, but the composites are allergic to less of a proportion of the whole. For example, 2 is, well, let's see. Yeah, because 2 is always going to basically be allergic to about half the numbers or a little more, because also 3 it's allergic to. And 3 is always going to be allergic to a little more than a third of the numbers. However, we introduce more and more composites that are allergic to smaller and smaller slices. Like, we're never going to meet another composite that's allergic to more things than 2. After that, the second place is always going to be 3. So on larger grids, even a number like 360 is only allergic to 359, 361, and its 24-ish factors. So that's about 20, I think it's 24 factors maybe for 360, something around that. And so it's, between 20 and 30 out of 360 numbers is a relatively small percent of them that 360 would be allergic to, and it would be one of the most allergic around its size to the most things. And so really the most allergic causing things, the ones that are allergic to the most, are the lower numbers. No matter how divisible a high number is, it might be more divisible than its peers, but it's not going to be more divisible than a super low number. And so I'm not positive about all these, where these almost alls go, or what vanishes, or if there's random grid sizes that just don't work because of the amount of numbers. But my gut tells me, and a small amount of investigations, and my gut tells me the only ones that don't work are pretty small. Now, here's a fun little sub thing. You could make a 1 by something, and you could think of it as a sequence of numbers. So the 1 by n case basically turns the puzzle into, you have a sequence of numbers that follows these rules, with the terms in the sequence before and after each other, because they can only be neighbors that way. Now, from a little investigation, I did find the minimum amount of numbers you need for it to work on a 1 by something, and I'm pretty sure that on all future 1 by somethings, there's at least one solution. pretty soon getting to the point where there's many solutions. But I need to run to the bathroom really quick. So look at this for a moment. And if anyone wants to, I'm just going to write, be back soon. Try 1D version. And I will say the solution to the 1D version right when I'm back in a minute or two. But first, feel free to leave it in the comments if you figure out what's the minimum size that a 1 by something works. The smallest n for a 1 by n. Remember that it's going to be 2 through 1 larger than that n in which numbers show up. Now, that's the reason why we start at 2. Because I could have made a rule that in multiple times here it says apart from the number 1. Or I guess it would mostly just be on the multiple of themselves apart from the number 1. But then 1 is also something that acts kind of prime-like in that case and doesn't really help the puzzles and is almost like a blank square that you just know the 2's not next to. So I was like, if I just start at 2, the rule's simpler. I mean, this first rule is a little trickier than if I said from 1 upward. But this rule's, the main rule is simpler if I start from 2. Because otherwise 1 couldn't touch anything. Everything's a multiple of it. So I'll be back very shortly. Leave a comment if you figure out the minimum 1 by something string, like a sequence, like string of numbers. For the minimum size, there's exactly 1 solution if you don't count it flipped. If you count it flipped, there are 2 solutions. Alright, folks, I'm back. So, what I said I would answer is, what is the 1 by n super simplified version of this? 1 by n's are a bit more trivial. When looking for solutions, I'm mostly looking at wider grids. However, the 1 by something is still an interesting question that brings it to the level of a sequence. And what I find interesting too is, well, if I can turn this grid puzzle by looking at the 1 by something case of it into a question about sequences, can I take any questions about sequences and turn them into grid puzzles? Go the other way around? Say, here's a question about sequences that exists. but it's just the n equals 1 case of this other type of thing we do on a grid. So that's an interesting possibility we could experiment with someday. But for now, looking at 1D version, starting with 2, the technically minimal one is just the number 2. I should have said the minimal one that's more... Okay, the minimal one is no string. No string technically follows the rules. Nothing is breaking the rule. But after that, the minimal one is just the number 2 as a single beginning of a string, a 1 by 1. That's also trivial enough. I should have said longer than that. We can note that 2 and 3 in either order wouldn't work. They can't be next to each other, and they're the first two we'd use. What about 2, 3, and 4? Well, 2, 3, and 4, 2 can't be next to either, and 2 is going to end up next to something. So what about 2, 3, 4, and 5? Well, 2 can't be next to 3 and 4, so it has to be on an edge next to just 5. 5 can't be next to 4, so it'd have to be next to 3, but that can't be next to 4. 4 can't go anywhere. So 1 by 4 doesn't work either. How about a 1 by 5? The numbers 2 through 6. With that, we can go 2, 5. We cannot go to... 2 is allergic to 3, 4, and 6. So we cannot put it in the middle anywhere. It would have 2 neighbors, and it only can be neighboring 5. And then after 5, that can't be neighboring 6 or 4. So that has to be next to 3. But 3 can't be neighboring 4 or 6 either. A 1 by 5 is not quite long enough. So good guess to our commenter guessing 5, but not quite. Because there's no way to fit all of those together. 1 by 5. Basically 1 by 2 through 1 by 5, as well as a 3 by 3, and I think a 2 by 1 through 6. I think those are the impossible sizes. I would be a little surprised if another size, or a 0 by 0, or 0 by anything. I would be surprised if any other sizes are impossible. Now, our commenter notes a string that goes 4, 6, 2, 5, 3. The problem there is the 2 and the 6. The 2 and the 6 cannot be touching each other. So it just doesn't really end up working. The 2 has to be on an edge because it can't touch 3, 4, or 6. It has to be 2 on an edge with the 5, and there's not a way of doing it. So good guess, or I mean, not quite guess, good construction of 1, but it breaks the rule in one spot. Now, to go a little longer, what about a string of 6? Well, now we're at the numbers 2 through 7. So now we have to take our investigation a little deeper. We have to go 2 could be it could be on the edge next to a 5, it could be on the edge next to a 7, or it could be between a 5 and a 7. And I'm only writing one copy of whatever would be the same as its flip. Like, I'm not going to write the flipped version of this because this is just telling me on the big scale so far that 5 is on one side, 7's on the other. So far, that string would just be flippable into the other. If I get a new piece of data of a new number, what matters is which side it's on. If it's on the side that already has the 5 or the side that already has the 7. But we're not going to write 7 to 5 because just those bits of possibility are just a flipped look at each other. Same with if 2 was on the other end. Well, yeah, then it would go 7, 2. So same thing. Now, so if we look at what has to come after these, 5 and 7 both can't touch 6. So no 6s coming around in the mix. Oh, and here I guess I should put a ... because it could continue onward there, possibly. These ones we said that's the beginning. These are the possibilities for where the 2 could go. So now let's say 6 isn't going anywhere. Our other possibilities so far would include 3 and 4. And so we're now left with a few different possibilities. This could go to 3 only, cannot go to 4. This one, though, we would maybe copy in our head. Now, this is the type of thing where when I'm calculating these, sometimes I'm copy-pasting the different paths and seeing what hit contradictions. However, if you were to think about them certain ways, you sometimes can do something more clever than having to copy paste so much. Right now I'm just trying to lead to this solution, but I'm curious if any of you have any breakthroughs. I'll mention some of the ones I've had, but along the lines of, oh, the eyes cannot be two apart, or things like that, that can give you shortcuts that don't make you do all the work of this. But just to make sure it's fully sort of demonstrated what the possible cases are. Right now, let's look at all the possible cases. Here we have a possible case where 527 was at the beginning, and then it goes to a 3. One where it was at the beginning, then it goes to a 4. And then we have one where a 3 actually came before it, and it wasn't at the beginning. So now, what do we have left in some of these cases? In this case, if we look at, we have a 4 and a 6 left. 6 can't touch either of these. 4 could get tucked right there. And 6 could get tucked right after. And this is good timing. I just saw a comment. It might be a little bit delayed from when the comment comes in or when the stream happens, but I just saw a comment come in that got this solution, which we have just shown works, in reverse. So Biofelis just commented the reverse of this, which is, the other possible solution. Now, these we haven't demonstrated can't be solutions, but if we look at these pretty quickly, we can see, okay, that can't be 6 or 4. We would need to stick a 7 there. And then we can't have the 6. We would need to... Oh, wait. Is this another solution? Okay, yeah. I guess when I first looked, I looked too quick and just found this one. For some reason, I was thinking in my head that when I found this solution earlier, that I had marked that the others didn't work. But I do believe this one works as well. So we have another... These are, so far what I've looked at, these are the flips of them are possibilities for 1x6s. And it's one of those things where I think a 1x7, or if not that, not long after, like a 1x8 or 1x9, will explode in how many possibilities there are. But right now we're at the cusp of that, the first size of a 1x something that's possible at all. So we may only have a few possibilities. Let's look at these others. In these cases, we've narrowed down the cases where it began with these things. Have we fully? Let's see. Well, let's see if we were to add something before them that's not identical to one of these. That's allowed, just to make sure we double check. But assuming these are at the fronts here, we have, in a lot of them, 4 and 6 left, or 3 and 6 left. And these ones also have a 5 left. Let's just go one at a time. This right here, following our 3, could be a 5. It cannot be a 4 or a 6. That's the only possibility. Following the 5, we're left with needing a 4 and a 6, and those don't work on either end of this. So this cannot be a string in a 1x something, because 4 and 6 can't fit on either end. So here we have, and just in case someone's new, let's try and keep this instructions in there as well, but noting we're trying 1D version. The less 1D versions are maybe a little denser, but it's still interesting to find all the possibilities when we're on the cusp of the smallest size of something that works. So looking at this one now, we're left with needing 3, 5, and 6, and 6 is the only one that works there. And 5 or 3 don't work there. If I put a 5 before this here, it's going to become a clone of this other one. So here we're left with just 4 and 6. Neither can be on either side, so that doesn't work. I think that's a flip of one of the previous ones we saw that didn't work. Now we're left with a 3 and a 6 in this one. And the 3 and the 6, the 3 can't go there, the 6 can go there, but then if we put the 3 there, it's a copy of this one down there that we already got. So we were assuming this is the beginning, because we tested the ones where it wasn't the beginning. And is that I just want to double check one thing after this, but here we can note that the 3 doesn't fit there, and if it fit there, it would be the duplicate, and if we tried to stuff the 3 and the 6 on this side, it wouldn't work. Now, the one thing I want to check, just to double check, is that there's nothing that works with where we have 7, 2, 5 that's not a flip of that. It'll probably end up being a flip of that, but just to double check that. If we have this anywhere in the number, then we can't have 6 come next. We need either 3 or 4 to come next. If I put a 3 over here, it's this thing in reverse is forming. If I put a 3 over here, then we would need a 4 and a 6, and that's not going to work on either of these. And yeah, the 3 here just ends up necessitating an inverse of that one. I'm pretty sure I'd already double checked this, but just wanted to make sure it looks right. So I'm almost positive now, but let me know if any of you for some reason find another, that these two or the flipped versions of them are the only solutions for 1 by 6 or reversed versions of these. And so that's the smallest size that ends up working there. It's interesting that they have 2, not counting symmetries of them, and the smallest size of 3 by something that worked had 2, the 9 one and the 5 one. So, what's happening? The table's getting big instead of other stuff. Okay, I think I fixed it. I hope so. How do I get past the table? There's like nothing past the table in the document, and it won't let me go out of the table. Whatever, that'll be the bottom of the document, the 5 one. Okay, so what other things, though, can we note about some of these sizes that I have done less investigations into? And as a reminder for anyone who's coming new, these ones I'm not going to answer until I make a main combo class channel episode about this. So these are for you to try and solve in the next month. Now, and they do each have exactly one solution. So here we have the eyes on the 3 by 5. And I want to investigate this because the 3 by 5 is technically the next smallest size that's not a 1 by something or 2 by something that we need to investigate. Because if it's at least a 3 by 3, the 3 by 3 itself doesn't work. And I believe I've fully investigated the 3 by 4s. I'll double check that more at some point, but I'm pretty sure that these are the only ones for the 3 by 4s. And so 3 by 5, there are ones that can work. And just to see how likely it is that they work, let's play a little game. Let's just fill in the ones on here with random-ish numbers and see if we can just make one that works. Let's say we want 2 and 3 kind of tucked away. We'll have that 4, 6 thing that works sometimes right there. These need to be odd around the 2s, so we'll put our 9, 11, and 13 right there. Let's put the 5 there to get it away. Oh, no, 5, 10, and 15 need to dodge, so we'll go 5. No, wait, let's see. 10, 5, and 15. Now, wait, 7 and 14 are going to need to dodge, so, I isn't a thing, so 7 and 14 being away from each other. Let's go, is that even going to work? Because 14 would have to be one of these two to be away from the 15. 7 can be there, and 14 can be there. Let's see, 2, 3, 4, 5, 6, 7. 8 doesn't have room. There's no room for the 8. So trying to put one together, even with some knowledge about it, it's kind of hard to stumble into one. And part of what I like about that is that for some grid sizes, it might be easier, maybe even too easy on big enough grid sizes, but on some grid sizes like this, a puzzle of its own is just find a solution. Find any solution, and that's the puzzle. And so that is a puzzle I will pose to you folks as well. Find any 3 by 5 or 4 by 4. And I don't know if we're actually going to encounter one today unless we get the full deduction, because as you can see, it's kind of hard to generate them. Let's try again. Let's put all the low numbers we can around here. Let's do 2, 5, 7, and 9, just packed around there. Let's get some more low numbers down here and try. But if all the lows are there, then the additive rule is going to be trickier. Let's make this one actually really big. We'll make that a 13, and that's going to be a 5. We'll put our 15 over there, and we'll put our 10 over there. We're just seeing if we can put one together. 4 and 6 will go there, and maybe an 8. Right? No, 8 can't touch 9. 8, that's the only spot left for 8. And so it would be 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, there's not enough. We needed to have made more room, but it's hard to, because now they're too close to each other. Like 14 would have to go over in one of these two, but then that can't. We also need 11 and 12. That's a big problem. 12 would have to go there. And then what if we switch the 12 and the 5 or something? Will that work? And then we would need to fit 11, 14, and 16. Can we do that? 16 would have to be up there. 14, no, because next to 15. So once again, even trying to generate one, it's hard to stumble into one on certain sizes. If any of you want to test, let me know in a comment later if you try this on bigger sizes, if you think it's easier to stumble into a solution on a larger size, which I suspect would be the case. Now on here, let's go back to trying to deduce things that we know about it so that I can formulate a little more info about not just stumbling into one by trying 50 times, but seeing what traits we guarantee about them. And that may give us clues about if we find solutions, which ones are more unique than others, or which ones are the only ones with a small enough set of numbers that would imply them as the only solution. Because one of the goals here would be, what is the minimum amount of numbers that can be filled in on a given size of grid and line up with a singular solution? I was surprised that it was as low as one number on the 3x4. I expect it'll be a lot more than one number on these sizes that are necessary to line up with just one solution. But I haven't found a solution on this one yet. I was just trying and I didn't stumble into one. So even just let me know if you generate a 3x5. I'm sure if I sat down and thought about we're going to generate them, we could probably make one. But the thing is, having more space doesn't always help, because this extra space does add on compared to a 3x4. The numbers 14, 15, and 16, and those are all composites. So compared to the 3x4, we have now given a new allergy to 7, to 3 and 5, and to the multiple or the powers of 2. So there's a lot of new allergies that are around when you have the 12 there. So let's note again for this size some things that we know can or can't be near each other. And mostly we begin with what can't be near each other and see if we can narrow it down to what can. So we note that 2, 3, 6, and 12 all can't touch each other. 2, 3, 6, and 12 must all be separated, so none of them are neighbors with each other. Now that's a little harder to use as our I rules, like I mentioned, on this size compared to like if we did a 4x4, because there's more different ways we could scatter non-touching things on this one that's harder to tile with 2x2 squares over it. We still can note these things because they'll be helpful, that those can't touch, and neither can 2, 4, 8, 16. Let's just skip the and know that's implied, so they're more clustered together. So these 4 must all be separated, and so must these 4. Some of these sort of overlap. 2, 3, and 4 also must be separated, but 4 doesn't have to be separated from 6, so we can't fully put 4 in that list. So what could this tell us? Now, let's actually add one more clue. We're looking at these eyes. What are things the eyes can't be? So, there are a lot of things we could note that for these eyes could cause a problem. And here's one reason. Well, there's two reasons. One reason is to be an eye, you need to have 8 neighbors. And that eliminates the number 2, because the number 2 is allergic to too many things in this range. If we imagine the minimal size of each thing that could be neighboring 2, they're 5, 7, 9, 11, 13, 15, and that's all that fits on this grid. That's only 6 things 2 could be neighboring. So it can't be an eye, can't be the nose either, can't be in the middle. So 2 can't be an eye, can't be an eye or nose. Nose. Okay, and put it in parentheses because we're mostly looking at the eyes right now, but having nicknames helps. Now, speaking of eyes, noses, and mouths, I'm glad that hopefully I'm talking normally, but I went to the dentist earlier today, and this half of my mouth was numb a few hours ago, so hopefully it's fully back to normal. If not, it will be soon. But here we can note 2 can't be an eye or nose, because there's not enough things that work to be all 8 neighbors. But what else couldn't be an eye? Because if you're an eye, either of these, they're symmetrical to each other at this point when we're just analyzing one number. Everything except a little 2x3 on the side is your neighbor. So anything that you're allergic to would have to fit in the 2x3 on the other side of you. For here, this would be the 2x3. For here, we'll look at it, that's the 2x3. So what if, for example, 3 was this eye? If 3 was there, we get a problem, because 3 is allergic to 2, 4, and 12. Or we could do the same thing with 2, 6, and 12. So those would have to be crammed onto this 2x3 on the side, but that can't fit 3 things that all have to dodge each other. So in fact, we can use these lists, I just realized, to look at that. These are essentially the numbers. There could be others we can deduce, but at least all these numbers cannot be eyes, I think. So none of those can be eyes, because it would stick the other 3 of their... I'm going to spell out 3 to say it's not the number 3, but the quantity. The other 3 of their list, the other 3 on their list, in a 2x3 spot on the side that couldn't contain them all distanced. There's a casual way of writing all this out. But there's an important note. None of these numbers can be an eye, because they're allergic to too many things that would have to be stuck in a small specific zone on the side. This one is unnecessarily big. We're just going to absorb it into here and say, oh no, we're going to go with this font size and say 2 also can't be a nose. Theoretically, 3 could be the nose for all I know so far. I don't know if any solutions line up with that, but I haven't disproved 3 being the nose yet. Because does 3 have enough neighbors? 3 would have to be around 5, 7, 8, 10, 11, 13, 14, 16. It has exactly enough. So let's see. If 3 is a nose, it contains, or its neighbors are precisely in some order 5, 7, wait, is there even enough room? 5, 7, yeah, let's see. 8, or wait, are there going to be 9 of these? 5, 7, 8, 10, 11, 13, 14, 16. Yeah, that's exactly 8. So if 6 is the nose, because we've already proven it can't be the eyes, its neighbors would have to be precisely these. Let's see if we could disprove that being possible. What would that mean? That would mean the ones that are left on the edges are the 2, 4, 6, 9, 12, and 15 would be on furthest left and right columns. So somewhere within the... Here, let's switch the order of these a little bit so that we can see our notes and the grid. Putting those down there. If 3 is the nose, its neighbors are precisely these, and that leaves these divided up among that square, those 3, and these 3 all together would have to contain these things. But 3 was a part of this list of 2, 6, and 12. 2, 6, and 12 are going to have to really avoid each other. Some of those are going to have to be in corners on the side. How could we even maybe note possibilities or impossibilities? Like, would 2 have to be somewhere particular? Would it have to be a corner? Because at that point, if 3 is the nose in this, seeing if we find a contradiction here, and because actually my gut tells me we might hit a contradiction, but I'm not sure. Let's see. If 3 is the nose, then could 2, or 2 is either, at this stage of equivalency with the symmetries, a corner or a non-corner, because it's somewhere in one of those 3 or one of those 3, and with the symmetry, they're just corners and non-corners at this point. So if 2 was a non-corner, that would mean that 4, 6, and 12 would have to be crammed on the other side, and that wouldn't work, because 12 would have to be touching either 4 or 6, and those don't work. So 2 can't be there. 2 would have to be a corner. Now let's see, would that even work? If 2 is a corner, what's next to it would either be a 9 or a 15. Either a 9 or a 15 would be below or above it. Let's shrink these. And what would that leave? That would leave the 4, 6, and 12 having some places we got to get them lined up. So 4 and 6 and 12, 2 of them would have to be in corners, and 1 would have to be there. I don't know. Maybe I'll go further down this rabbit hole in a minute, but sometimes I go down a rabbit hole, don't hit anything yet, and I'm like, let's test something else instead. We'll keep this note about 3 doing that for later, but there are other things to test other than if 3 is the nose. So, for now, what we know, for what the eyes, back to those, can be, possibilities for eyes. I haven't disproved 5 yet. I feel like 5 might be too small to be possible for an eye. It's allergic to a lot of stuff, but let's think real quick. 5 couldn't touch 4, 6, 10, and 15 in this range. And those could fit on the side on their own, so 5 might be possible as an eye. So we have... And let me see, there was one size that I did randomly create one just to see what it was. Give me 1 second. I want to see in one of my other documents. Or no, I'll look at it later. But there's one, I forget if it's the 4x4 or the 3x5 or maybe both, that I did find at least one solution for. And I was curious what the lowest number that is an eye. But I don't know the lowest possible because I haven't fully completed any of these investigations. I've been doing a lot of different puzzles for fun that I've designed recently, and this one I'm just going extra deep on because I really liked the 3x4 having just a few solutions before it exploded, so I'm looking for more interesting stuff. And because I've learned a lot about what makes this type of puzzle work in general or not work. A lot about mathematics and games. But for now, possibilities for the eyes. They can't be numbers on these lists. So far, they could maybe include 5, 7, and I haven't proven these are the possibilities. These are just definitely not contradictions. So 5, 7, 9, and 10 isn't on those lists. That also seems like maybe it wouldn't work as an I, but for now it's not on those lists. So these are things that I's could be, but the I's are 2 of these, and they can't be 2 that have any of these rules. They can't be 2 apart in size. They cannot be multiples of the same n, larger than that n itself. They cannot share a multiple in the range. That's not going to be a problem. The sharing a multiple in the range is not a problem for any of these. However, they can't be 2 apart is pretty notable. A lot of these possibilities look like, oh, what about that and that? What about that and that? We can't have the I's be 2 apart. Otherwise, the number in between them, not between them as in the nose, but the number in between their size, if they're 2 apart in size. Oh, that's ironic, because the I's cannot be 2 apart in size, despite being defined by being 2 apart spatially. So that I'm just making that as an ironic note because it's kind of funny. We define these I's as they're these spots that are 2 apart. But one of the things we can prove are that they can't be 2 apart in size because the number in between their size would have nowhere to live. So a lot of combos of these actually don't work. It's not every pair of these that could work as I's because, for example, 9 and 15 can't both be I's because 3 would have nowhere to live. Let's see. 5 and 11 can't both be I's because 10 would have nowhere to live. So it's like some of them get pretty limited. Like if 5 is an I, then the other can't be 7. The other could be not 7, that's 2 apart from it. 6 would have nowhere to live. With 9, 10 would have nowhere to live. With 10, does that work? 5 and 10 being the I's? It seems like it wouldn't because they're like, that's a multiple of that. But it takes care of that, so it already had somewhere to live. So maybe it could be 10. Funny enough, 5 and 10. 5 and 11 doesn't work because 11's neighbors with 10, and if we didn't put the 10 in yet, it would have nowhere to go. 5 and 13 could work. 14 doesn't work because 14's neighbors with 15, and 5 is a factor of it. 15 does work, actually, maybe. Not like I know there's a solution, but we haven't disproved it. So these are the only things that if 5 is one of the I's, the other I could theoretically be. And some of the others are a little less limited, but they all have some. They can't be an I along with. 15 can't be an I with 13 or 9, or maybe other stuff, or maybe that's all. So, what things could be pairs of I's? It's interesting to go down this rabbit hole. Now, let me take a peek at what time it is. It's been about an hour and a half. Now, BioFella says, I think if you spin sequences around primes, you might be able to find solutions faster. I don't know what you mean by spin solutions around primes. If you mean like we are rotating solutions, we're sort of accounting for rotated ones. Like, for example, by saying any note about the I's, so far we've just proven about one of the I's. We're accounting for transformations of it. Like these, when I had them labeled with letters to show those symmetries, the I's had the same letter. Once we have a few things on there, flipping it, or you could create a new solution, but a few things being written on there in particular spots can tie down one of the orientations. Like if I say, that's there, that's that, that's that. Now we've pinned down which orientation it has to be. So I'm not sure exactly what you mean by spin sequences around primes, but feel free to elaborate. Wade notes that since the puzzle is allergy themed. Okay, so I should note, the puzzle's not actually allergy themed. I just like using nicknames. And so allergic to seems like a good word for has to dodge. And so, or can't be neighbors with. Allergic to was just a casual nickname I thought of, I think today, or if not today, yesterday. And not necessarily the theme of the puzzle. I've been thinking about what I would want to call this puzzle. I don't know exactly yet. I haven't settled on my perfect name. So for now, you can call it my factor grid puzzles. And if you needed to clarify, you could say it's a factor grid puzzle where our rules are that neighbors cannot be multiples or one apart. And if you wanted to be extra clear, you could note that we are using consecutive numbers from 2 upward, but I'll give it a clever nickname sometime. I like your idea of Wade says we could call it histamino, or histamino, because there's ominoes are a suffix. Well, it's a loud train. Ominoes are a suffix that are for things like pentominoes and tetraominoes that work in a lot of puzzles. And that could be a good name, but it's not quite allergy themed enough, and it's not quite pentomino or tetraomino themed enough. So while I like the nickname Wade, I'm going to keep brainstorming in my own time what perfect name I should give this puzzle. For now, I think of them in my head as number grid puzzles or factor grid puzzles. And good luck, Wade, with the geometry test you noted. Awesome that you are done working. Good job on making a good geometry test for your class. That's cool. Feel free if you ever want to comment any, just like 1 or 2 examples of any problems you put on there. Don't feel obligated, but if you want, it would be interesting maybe to leave 1 or 2 examples of the type of things your students are working on in geometry. And we also have an older note I didn't reply to in the comments, and there's 2 older notes to reply to. One is, it's Othello-like, and it has some things similar to Othello. I actually saw a new game that was nicknamed Yin Yang online that was quite Othello-like. And later we'll do more random puzzle variety of pre-existing puzzles in another live stream. That's always fun to explore the wide world of pre-existing puzzles, although I haven't found any quite like these ones. It's hard to even find any types of puzzles that rely on using 1 copy of each number in a larger range, as opposed to we use 1 through 9 times or something like that. And we also have a note from George Washington earlier in the comments that says, what's the likelihood the 6 unsolved Millennium Prize problems will ever be solved? I'm going to say, well, we don't know. It's a mystery. But I'm going to say it is highly likely that some, but not all of them, could be solved. Some problems turn out to be unsolvable, or the formulation of math sometimes changes in a way that renders a question not even sensible as a question. Like the language it was constructed in was not cohesive enough. So I would say there's a good chance that in all of the time of humans and ancestors or descendants beyond humans, that some but not all of those will be solved. However, that's not guaranteed. We could never solve another, or we could solve all of them. The story of Grigory Perelman, the person who solved the only one of the 7 so far that has been solved and declined the $1 million prize, is a very interesting story I've told brief bits about in live streams and stuff before, but someday I will make a whole episode analyzing sort of half the mathematics and half the humanity and philosophy behind that story, because that is an interesting story, the solving of the Poincaré conjecture, which is the one of the 7 that was solved. Now, as far as those Millennium problems, I have read a book about them as well as other resources, and I find them very interesting. And someday I would like to make a whole episode that gives a brief overview of all 7 for viewers. And I also like the idea of slowly diving in to one at a time, at least some of them. And one of them is the classic Riemann hypothesis, which is by far the most likely to be something I make a whole episode just dedicated to one Millennium Prize problem in the near future. Not super near future, but the one of them that I would turn into a whole episode because I know enough about it, out of those remaining 6, that I would do that in the near future, is the Riemann hypothesis. Later on, maybe I will know enough about some of the others to turn those into episodes as well. But the Riemann hypothesis would probably come first, or possibly a quick overview of all 7. Now, if I do an episode about that, it's actually not just going to be 7. There are more than 7 problems that have been awarded $1 million or more prizes in mathematics. So we would actually do a list of about 9 or 10 million-ish dollar problems from math history, 7 of which are grouped together in one set. Now, similar to the Millennium Prize problems, another thing I would love to make an episode diving through all of, when I understand a few of them a bit more, I don't understand all of them in depth, is other lists of mathematical problems that have been written at notable times, such as the list of Hilbert's problems that inspired the Millennium problems. So Hilbert's list of big questions of mathematics that he published was very foundational and included this whole web of problems, some of which have been solved, some of which, like I hinted about the Millenniums, have either been rendered obsolete or shown that their answer is independent of the system or unprovable or things like that. Some of which have been solved or proven or disproven, and a lot of interesting open questions among those as well. So maybe we'll do an episode about Hilbert's questions sometimes too. And Wade also mentions the Goldbach conjecture, which is another really simple to state but difficult to crack problem. Now, we have been going for quite some time. It has been over an hour and a half, and I do believe I'm going to wrap up this stream soon. I really enjoy looking at these notes, and I'll be looking further in my own time at all of these things, creating more notes and details I can prove about different sizes. But I mostly wanted to give you folks 2 things. One was a chance to try a few of these problems yourself and see if you can solve them with any clever techniques or even just solve them at all. And also to give you folks a little look at some of the type of research, in quotes, that I do in my more casual type of research. Some of the more casual end of mathematical investigations that I like to do. So I will develop more of these puzzles before long, and like I said, eventually in grade -3 at some point. Probably after my episode about star battles, though. There will be an episode about grid puzzles that I have invented, and that will include the solutions of these, as well as whatever cool stuff I have discovered about these since then. Now, this is all about grid puzzles for a little while, so feel free to leave any comments on this video later if you discover anything cool about this or have any thoughts. But for now, I'm ready to move on to other topics. I will continue having fun with these in my spare time because it is a current little side obsession, but I'm also mostly working on some other 3 related mathematical episodes to begin grade -3. And as I said, that whole part of the classroom that I'm not showing yet has some cool things. And make sure you are all tuned into my combo class channel as well, where the main intro episode will be coming out in less than a week, and where the last finale also was posted. Now, Biofellis left something they say, I think that's it. I'm not sure exactly the formatting you're using there. Leave maybe a little more, or yeah, leave it as a few lines if you want to make it look like a thing. But also let me know what size you're solving. But if that's one of the other ones, that's cool. I am going to end the stream soon, so maybe hold the thought if you want Biofellis, or repost it there as well. On the main video, remember, the live streams get processed like videos afterward, and you can watch them just on the live tab whenever. It doesn't have to be live. So anyone else can feel free to comment there if they find anything cool, or have their own solutions, or even their methods of solving it. And Biofellis says they think they found one for 5x3. So I will look at that later and check it out, see if it seems to fit all the rules. But to note, there are probably, my gut tells me, many solutions for 3x5. So anyone else can also comment other ones they find or rules they can find about what can or can't be part of a solution for a given size. So I will come back to this another time. I'm going to wrap up now. Stay tuned for all of that combo goodness. There will be more shorts and stuff coming on this channel soon, but the big thing I'm working on now is on my combo class channel, the first few episodes of grade -3. And if you do want to go further down the combo rabbit hole, there's the Discord server linked in the description. And if you want to help out with grade -3, make sure we have an extra awesome start to our grade. There is a Patreon for people who are able to support, or the YouTube memberships on here. And that's about all for today's stream. Except for, let me see, maybe we should take a quick look at the moon. The moon is so beautiful tonight. And in fact, let me look this up real quick. There's something interesting about the moon. So this thing called a supermoon occurs that is a mildly vague term, but they standardize it by being within a certain percentage of something. And it's when the moon is closest. And the moon looks extra big on a supermoon. And it's when it's within some percent of the closest point it could be on the way the cycles line up. Supermoons, when I looked it up earlier today, happen 3 or 4 times a year in total on the planet. And the supermoon occurring, I believe it's here, is the moon looks big. I believe it'll be visible here. There is some news if you look up supermoon. It's going to be the last supermoon of the year, coming, I believe, tomorrow. Tomorrow night will be a full moon, but it'll be an extra special type of full moon. And so look up supermoon if you're curious about that. They also note that it's the extra special beaver moon. I looked that up. What that means is it's a nickname for a certain type of full moon. It's the full moon that comes in November because that's when the beavers are doing something special. There are sometimes nicknames, like a blue moon is when you get 2 full moons in a month, I think. And there are various nicknames like that. This one's called the Super Beaver Moon, or AKA the Beaver Super Moon. And that's pretty neat. And since the moon is so large and magnificent right now, let's take a little peek at it. I'm vanishing for 1 second, but I'm going to bring you folks over to a view nearby where we can see the moon. I've been taking a lot of walks to see the sunset in areas around here, and it's very beautiful. But even at night, once the sun's already set, right now the moon is looking pretty neat. And let's return for a second. And I don't think you're going to be able to see it very well. It causes weird light things. I've been trying to film the moon, and even on my better camera, it's really hard to see. But there is our almost beaver supermoon. Let me zoom in a lot into it and see if we can somehow get that spiky glow to go away. It's funny. It's doing the thing that some people's eyes do more than others in the dark. Like, do your eyes do that when you see headlights on a car in the dark? Because mine do. But it turns out not everyone gets it very bad. Some people barely have it, and some people get that really bad. And the camera's doing it. But there's our almost beaver supermoon. Okay, back to the classroom to do our final wrap up. Hope you all enjoy the moon wherever you happen to be, if you are able to get a view of it. Or maybe it's too cloudy and you'll have to see it next time. We'll do some more thoughts about that another time, but I probably won't be live streaming tomorrow, so probably that's our last picture of the moon for a moment. And I think that's all for now. I'll catch you all again soon. Love you all so much. And please do some investigations on grid puzzles on your own. Let me know what you discover.